In the final unit of applied chemistry, you're going to be learning about what you call redox reactions and also about electrochemistry. So in the first lecture, I am going to first be talking about reduction and oxidation reaction. So a special type of reaction is called as you may be able to guess, a reduction-oxidation reaction, also known as a redox reaction. Now, many of the equations that you have already studied, you learned about this in general chem either last year or the year before. We learned about single replacement reactions, synthesis, and decomposition. And those are all examples of redox reactions. We didn't call it that, but now we can give it the special terminology known as redox reaction. Reduction means gaining electron. Oxidation means losing electron. Okay, a helpful way to remember is the acronym oil rig. This means that oxidation is losing, reduction is gaining. Okay, once more, oxidation is losing, reduction is gaining. Now, in order to determine what element is being oxidized or reduced, we use something called oxidation numbers. And oxidation number rules, there are many of them, but we're going to keep it really simple for this class. There's only four major rules that you really need to know for this unit. The first one being that the oxidation of a free element in its elemental state is zero. An example being like iron solid or hydrogen gas or something like liquid mercury. The oxidation number of an ion, such as Fe3 plus or Ag positive, would be equal to whatever the charge is on that ion. Okay, and then hydrogen usually has an oxidation number of +1 when it's part of a compound, and oxygen has an oxidation of -2, oxidation number of -2 when combined with another element. And there's many sorts of exceptions to these rules, but we're only going to focus on these four to keep everything simple. So let's look at some of these examples of oxidation number. Okay, the oxidation number of silver in Ag solid is, if you look at the previous slide at the notes, you'll see that the oxidation number of any element by itself in its elemental state, silver being a solid in its elemental state, it will have an oxidation number of 0. Okay. The oxidation number of iron, Fe with a 3 plus charge, that thing should be an exponent, that's an ion. So the oxidation number would be equal to whatever the charge is on the ion itself, in this case being a +3. Now take a moment to look at this next one. The oxidation number of hydrogen in H2, again, like the silver example, okay, hydrogen exists as a gas, and when it's by itself, its oxidation number will be 0. Okay. And then looking at this last example, the oxidation number of oxygen, if it was just O2, it would have an oxidation number of 0. But since the oxygen is combined with iron, it has an oxidation number of -2. So how do we use oxidation number? If an element increases in oxidation number over the course of the reaction, that means that the element is losing electron which means that it is being oxidized. Okay. By the same token, if an element decreases in oxidation number, that means it's gaining electrons, which are negative, and that element is therefore being reduced. It's very important to note that every redox reaction has something being oxidized and something being reduced. Okay, you can't have one without the other one happening. Okay, so take a moment to go ahead and write the oxidation number of each of these items as you move forth. So pause the video and write down the oxidation numbers. So if you did these correctly, these are the oxidation numbers that you could have gotten for each of these species. And as you can see, the Fe went from an oxidation number of 0 to +2, which means that it is being oxidized. zinc, on the other hand, went from an oxidation number of +2 to 0, which means that it is being reduced. And terminology is very important. You need to say that it's the element specifically that is being oxidized or reduced. You wouldn't say the Zn2 plus is being reduced. We say that zinc, the element, is being reduced. And that's just a matter of just convention and terminology. So in your time in chemistry, you've learned how to balance general chemical equations, and earlier this semester you learned about balancing nuclear equation. So in this unit, you're going to be learning about balancing redox equation. The main objective is making sure that the charges are balanced on both sides, aka that the number of electrons gained by one is equal to the number of electrons that's lost by the other. So here's the general step for balancing redox reactions, and again, we keep it really simple in this class. You're going to first separate into two half reactions. You will add appropriate number of electrons to the side that requires it, and you'll see what I mean in a moment. And then you want to make sure that you multiply the equation by common multiples so that the electrons will cancel. And then finally, you add the reaction together and canceling the electrons as needed to give the overall equation. So with that in mind, let's go ahead and go to the first practice. Okay, let's try balancing this equation. You can see that we have silver and iron 2 plus going to silver positive and Fe. So the first step is to separate it into two half reactions. So by that, what we're going to do is we're going to go ahead and put Ag solid goes to Ag positive. And then the other one would be Fe2 plus aqueous goes to Fe solid. Now the second step is to add electron to the side that is needed. And one thing that can really help you is determining the oxidation numbers of each of these species. So in the case of the Ag, that is an oxidation number of 0. Well, this one has an oxidation number of +1. And then on the other one, the Fe2 plus has an oxidation number of +2 or 2 plus. And the Fe has an oxidation number of 0. So we add electron to reduce the positive so it's in line with 0. So for the first one, you would add 1 E negative. Okay, and hopefully that makes sense to you, so you can see that the +1 on the Ag and the -1 on the electron total combine to an overall charge of 0, which matches the oxidation number here of the silver solid on the left side. So for the Fe half reaction, we should add the 2 electrons over here. And notice this 2 because we have here a 2 plus going to 0. So when you add the 2 electron negatives and plus 2, that would give you a overall charge of 0 on this side. Okay, so step 1, separate the half reactions. Step 2 is to add the electrons as needed. Step 3, the electrons should be canceled, but in this case, the first half reaction only has 1 electron involved, while the second reaction has 2 electrons involved. So what we want to do then, to make sure that these electrons end up canceling, is we are going to multiply this silver equation by 2. So when I distribute that 2, you get 2 Ag solid yields 2 Ag positive aqueous plus 2 electron. And now you can see that the electrons are the same in both half reactions, and as a result, we can go ahead and cancel these. Okay. Now, to write the overall half reaction, we take the reactants of what's left over and combine them. So it becomes 2 Ag solid plus Fe2 plus aqueous. That's going to go on the left side. And the 2 products remaining would be 2 Ag positive aqueous plus Fe solid. And that right here would be your balanced redox reaction. Okay. So if you think you're ready, let's go ahead and try your own example on the next slide. So just go ahead and take a few moments to try this yourself. So you may pause the video at this point, and then you may resume when you feel like you are ready to check your answer. Okay, let's see if you got this first step correct, which was to separate it into 2 half reactions. And then go ahead and pause the video and try the next step. So using oxidation numbers, we determined that we needed to add 3 electrons to the first half reaction and 2 electrons to the other half reaction. Okay, so now go ahead and try the third step and pause the video. Now, hopefully you were able to tell that you had to multiply the first equation by 2 and the second equation by 3. So in doing so, you end up creating a total of 6 electrons that are transferred in the first half reaction, and 3 times 2, 6 electrons also transferred in the second half reaction. Okay, now go ahead and combine these equations and pause the video and then check your work. So when you combine these 2 half reactions, this should be what you get overall. Notice that you want the electrons to cancel, which they do in this case. And make sure you take note here that the chromium went from an oxidation number of 0 to 3 plus, while the zinc went from an oxidation number of 2 plus to 0. So that means that chromium was oxidized while the zinc was reduced. Okay, so that concludes the first part of the lecture for the unit. So when you're ready, you may move on to the second lecture.